In this video, we're going to derive the surface area of a frustrum. Now, a frustrum is basically a part of a cone, right? This is what a frustrum looks like. It's a part of a cone, but it does not include the pointy part at the top, right? If this were a cone, then we would have some point right there, and we could extend it to these two sides. And so this full picture that we have right here would be a cone, right? But the frustrum is basically the blue part of our drawing, where it basically has two circular bases right here. And we're going to say that we can of course measure the two radii. We can measure the larger radius and the smaller radius. We're going to say that the larger radius has a length capital R, and the smaller radius is a length lowercase r, right? And we're going to say that this length right here is capital L, right? So these right here are three dimensions that will define any given frustrum, right? Any frustrum can be defined by these three things, right? And so our whole goal is to find the surface area of this frustrum in terms of these three dimensions, right? So we're going to find the surface area of our frustrum in terms of R, and L. So R, and L. So that's it. That's pretty much what we have to do. Now, when I'm saying we're going to find the surface area of the frustrum, we're not going to include the areas of the circular bases. So we're not going to include this area right here. We're not going to include this area right here. We're including the area right here, like the surface area of our frustrum, right? It does not include the circular bases. So how could we find the surface area of a frustrum? Well, it turns out if we were to unravel the surface of this frustrum, we're going to get a two-dimensional shape, because when we unravel it, we're turning this into two dimensions. And so what we're going to get is something that looks like this, right? Right, we're unraveling it, and you're going to get something that looks like this. And it turns out that what this is going to look like is it's going to be part of a circular sector. In fact, if you were to unravel a cone, right, if you were to unravel this cone, right, this entire thing, then what we're going to have is we're still going to have this point right here. It's going to extend to both of these two sides, and really, this right here is a circular sector. So if you were to unravel a cone, if you were to unravel the surface of a cone, you would get a circular sector. Likewise, if you were to unravel a frustrum, you would get this part of the circular sector. So, next thing we should do is we should probably translate these measurements onto our blue drawing right here, right? So, pretty much we have to think about what happens when we're unraveling our frustrum. Well, when we unravel this surface, well, L right here is still going to be this length L right here. So this is still L. But what happens with our radii? Well, when we're unraveling this frustrum, what's going to happen is the circumference of our bases, so the circumference of our larger base is going to become this length right here. So this length right here is just going to be 2 pi capital R, right? And when we're unraveling it, the circumference of our smaller base right here is going to become this length right here. So this will be 2 pi lowercase r. And so now we have translated our dimensions onto our two-dimensional drawing of our surface area, right? So what we have to do is we have to find the surface area of the frustrum, which is of course this area right here. And that's the same thing as the area of this part of our sector. It's the area of this blue part of our sector. And we're going to call this area just A. So we have to find what A is. And what we can do is we could find what A is by subtracting the area of our larger sector minus the area of the smaller sector. And that would give us this blue area right here. All right, we're going to say that the area of the smaller sector is A sub S, because S represents the smaller sector. And we'll say that the area of our larger sector, right, the entire thing, the area of our larger sector, all right, AL, is what we're going to call it A sub L. Pretty much it's going to be the area of the larger sector. All right? So A sub L corresponds to the area of the larger sector. So now that we know that, what that basically means is that, of course, what I just said, the area of our the blue area is going to equal the area of the larger sector minus the area of the smaller sector. And so this is really what we have to find. We have to find the area of the larger sector and the area of the smaller sector. But how do we find the area of a sector? Well, if you remember, to find the area of a sector, we have to know the angle that forms that sector. So we're going to call this angle, we're just going to call it angle theta. And we also have to know the length right here that pretty much the length that the sector is pretty much at, right? The radius of our sector, basically. And so we would have to know the radius of our smaller sector and the radius of our larger sector, which both involve knowing this length right here, which we don't know it, right? We're just going to call this length x, right? So remember, we have to find the surface area of our frustrum in terms of r, and l. We don't want them in terms of theta and x. So what we have to do is we have to find what we have to find what theta and x are in terms of r, and l. That's what we have to do first. And so that's what we're going to do, right? All right, so basically right here, we're going to find what x is in terms of r, and l. And so to do that, pretty much what we could do is we could actually say, well, if this length right here is x, it turns out that, remember, when we're unraveling a cone, really this is x, this will also be x. So we're going to label this as x. Now there's something really interesting for what we've done here. Turns out what we could do is if we establish the height of our cone right here, then what we actually have is this has to be perpendicular and this has to be perpendicular, right? Right, because these two, like this radius is horizontal, this radius is horizontal, and our height right here is vertical, so they have to be perpendicular. And because these are perpendicular, notice how these right triangles are similar to each other, right? They both contain this angle right here, right? And they both have two right angles. And so as a result, this right triangle right here is similar to this right triangle by angle-angle similarity, which means we could say their side lengths are proportional to each other, right? And the reason why that's useful is because we could say that x over r is equal to L plus x over capital R, right? So I'm just going to write that. X over r is equal to L plus x over capital R. And so this works because we know that their side lengths, right, or their side lengths are proportional to each other. And so all we have to do now is solve for x, and we have x in terms of r, and l. So basically we should cross multiply first, right? So what we get is cross multiplying, we get rx equals r times L plus x, right? Expanding the right side. Right, and then I'm just going to subtract this to the other side. Actually, what we're going to do is we're going to move to the other side because it just kind of looks weird going all the way to the bottom. We won't have to do that. So I'm just going to move up to here. All right, I'm going to rewrite what we have. We could subtract rx to this side. Right, and then we could factor out x. Right, and then we could divide r minus r to the other side. We get x is equal to this. Right, this would be it. This right here is x. So we have now found x in terms of r, and l. That's it. And next we have to find what theta is in terms of r, and l. All right, so that's what we're going to do next. Right? To find theta. So how do we do that? Well, it turns out it's actually much simpler because right here we could think of theta and relate it to arc length of a circle. Because if you remember from geometry, like this is going to be a basic formula right here. It's a basic formula. It's not specifying any dimensions that we've done here. But the basic idea, if you remember, is theta equals s over r, right? And so we can use this idea to find what theta is in terms of r, and l. So, really, all we have to do is let's just use this smaller sector right here. Well, the arc length is 2 pi r, and our radius, r, is really x, right? That's it, because we know what x is in terms of r, and l as well, So really, this is as far as we need to go. Right, so that's a 2, right? That's it. Now we're ready to find what the area is. So to find the area, pretty much it's the area of the larger sector minus the area of the smaller sector. So really, I'm just gonna write over here, what is the area of the larger sector? Right, the area of this larger sector. We know to find the area of a sector, right, it's just gonna be theta over the full 2 pi radians of the circle, right? Theta over 2 pi times the area of the circle that forms this larger sector, which is just going to be pi times the radius squared, or pi times L plus X squared. So this is what we get when we find the area of the larger sector. All right, and then we subtract this by the area of the smaller sector, which is just this area right here. And we, again, it's the same idea for finding the area of a sector, right? Right, and it's going to be as theta over the full 2 pi radians of the circle, right? And then the area of the circle that forms this smaller sector is going to be pi times the radius squared, or pi x squared. And so this right here is really what we get. And notice how pi will actually cancel out in both of these places. And we can factor out theta over 2 from both of them. So that's what we're going to do. So we factor out theta over 2. And we're going to get L plus X squared minus X squared, right? Because that's what we get when we factor out theta over 2. It's this minus that. All right, now, turns out, what we're going to do is we're actually going to, I'm just going to show you a quick algebra thing. All right, when we expand L plus X squared, right, we're just going to look inside these brackets, right? Really, you have L plus X squared minus X squared. Really, L plus X squared, that's L squared plus 2LX plus X squared, right? You could FOIL this out for yourself to figure out that this is true, right? And you just subtract X squared, and notice how X squared and minus X squared cancel out. So this right here is just 0. So this right here doesn't even matter, it's 0. So really, this right here is what we're left with inside the brackets. So that's what we're going to write. Yeah, just erase this. Yeah, this is what we're left with, so. And that's what we're gonna write inside these brackets. Theta over 2 times L squared plus 2LX. And now at this point, we are able to substitute for X in theta, right? We're able to substitute theta for what we have here, except there's something going on here. Notice how it's theta over 2. But really, if we were to do theta over 2, really that 2 isn't going to be there, right? And so really we have to write theta over 2 as pi r over x. So that's what we're going to do. So really, what this becomes, theta over 2 is just pi r over x. And of course we still have L squared plus 2LX, right? So this is what we have, right? Now we got to substitute x for this stuff, right? So x, we know we have pi r over this stuff right here, which is r all over r minus r L, right? That would be x. And it's multiplied in brackets L squared plus 2L times this stuff, or just r all over r minus r L. And so this right here, we've now substituted x for what we have right here. And so this is right here, it's kind of our answer, but we just have to simplify it now, right? So simplifying this, right, we still have pi, but notice how, I'm gonna do it like this. R and R cancel out, don't they? And the r minus r gets moved to the numerator. So what we get is, right, r minus r gets moved to the numerator, so we get r minus r here, and L is still in the denominator. Right, and notice how inside these brackets, we get L squared plus 2L squared times r all over r minus r. Now, here's something that you have to realize. It's the fact that this L will cancel out with these two L squareds, right? We know L squared over L is just going to be L. So, really, this cancels out with L squared, and we're left with a 1 there, and we're left with a 1 there, right? So that's really what happens. And so we can also factor out L to the front. So when we do that, we get the area is really pi times r minus r L, and inside these brackets we get 1 plus 2 times r all over r minus r. And so this is what we're at now. And so now we just got to distribute this across, right? That's all we have to do now. Right? And so when we do that, this times 1 is just going to be what we have right here. Right? And now we got to multiply this by this. Okay? So let's just focus on what we're multiplying, because this might look a little weird. So we're multiplying this thing by this thing. Right? So notice how r minus r and r minus r will cancel out. So this won't be here. So we're going to get pi L times 2r, or just 2 pi r L. So that's what we get. And so at this point, we can factor out pi L, right? Pi L from both of them. And we factor out pi L, we get r minus r plus 2r. And really, 2r minus r is just plus r. So really, we get pi L times r plus r, so capital R plus lowercase r. And this is basically it, but really the way that people like to write the area of this is they like to write it like this. And so this right here would be the area, or it would be the surface area of this frustrum right here, which of course we know we're talking about this surface area right here, not including the areas of these circular bases. This right here is basically the surface area of a frustrum, and that's pretty much the whole idea. We had to basically unravel the surface of this frustrum and come up with something like that. We had to draw some relationships between triangles. We had to know arc length, and then we use area of a sector. We substituted this stuff into here, simplified it, and now we're at our answer. This right here is pretty much the surface area of a frustrum. That's pretty much it.